Hello, this is Jeremy Hong from Hong's Electronics, back with a video that is hopefully better video quality and better audio quality. I got this mic overnighted. This is at least one that I've seen is very popular and appears to be very high quality from the 1 minute that I've listened to it, and also did the recording initially. So once again, this is part of the series on the ADP5470 behind me here, from three different perspectives. So today we're going to talk about from the standpoint of an academic. So that is whether you're a graduate researcher or just a researcher at an institution, or lab manager that's looking to outfit your labs for your undergrad and graduate courses, or a professor that's either collaborating with a lab manager or trying to outfit a lab for research or for classes. Once again, this unit was provided by Digilent. They are sponsoring this video series. Yeah, so circuit theory is a pretty obvious thing that this covers, right? So everything from Ohm's law, your RLCs, right, op amps even. In circuits 1, we either had the choice of signing up for like a more traditional lab or with the National Instruments MyDAC. Now, by this point, again, I had already had the analog discovery, the original one, for at least like 8 or 9 months, and had used that because, right, it was literally one of the things that I purchased the moment I got a .edu address email. Eventually, I did run into it in, I think, devices and circuits. I'm trying to remember when I actually used the NI MyDAC, but from my experience with it, didn't like it at all. Also, the price tag was just right. It was a little high, so it's not something that I particularly wanted to own either. And so I ended up using even like I was the guy that, like, at the time, because I worked under the lab manager as a lab assistant maintaining all the different EE labs. I would usually, before lab, already assemble like my breadboard for like the circuit, and then do a couple of cursory measurements and stuff, make sure it works, and then with my analog discovery, and then take it to lab, do the measurements there, write the lab report, and then come back. And then circuits 2 is basically devices and circuits, so that's like transistors, MOSFETs, more like your active devices, your primitives for those. And then circuits 3, which is technically an optional course because it's usually a focus area track. So that's when you pick your specialization. So for me, it was electronic systems, so it was part of circuits 3 was a part of my track, and circuits 3 was primarily focused on op amps, active filters, all that sorts, right? It's pretty much just an op amp course, and this instrument definitely would cover handily all three of those cases, or all three of those courses essentially. The other part is, right, anything mixed signal, this thing will pretty much excel at, especially this model or the 500 megahertz model. Once again, I feel very strongly about the fact that this one instrument can pretty much cover, like, right, you almost only need like one, circuits lab, and then throughout the week, right, you just have students in and out from all different courses. Of course, from the lab manager perspective, adds risk because having one lab with just one piece of equipment, right, can lead to all sorts of interesting problems with, oh, what if all of them blow up at once, right, during the first week without fail? It seems like all the undergrads in circuits 1 put the multimeter in parallel with their circuit, so right, they'll just basically just measure with the ammeter function in place right across the terminals, essentially across the power supply, right, thus creating a short and burning out the fuses. So Right, it's a valid concern. So this guy, right, the fuses are easily replaceable. They're on the bottom, and aside from that, I mean, hopefully you'd have a few spare units of these. So that's pretty obvious. And then given again, I haven't torn this down. I kind of don't want to tear this down because I plan on using this quite a bit. Uh, EEV blog has a video from like 7 or 8 years ago. I mean, it's a while ago on the NI Virtual Bench, the 350 megahertz model of that instrument, and I think basically this is just a rebadge of this. And from what I understand, it's pretty robust in its construction, and there's lots of added protections. So blowing out like the front end of the scope or the digital channels is kind of, I mean, it's pretty difficult from what it appears to be. It's pretty student proof, but again, right, like it's kind of a lab manager's job to assess what right, the needs of the lab, the risk associated with that, right, and then of course balancing that with professors and potentially even some student feedback over the years, right, or over time. So, right, like I could foresee this being used for both your basic circuit sequence as well as digital electronics, because right, logic analyzer, it's kind of a given, right? Like this has enough channels that pretty sure that it could cover almost any digital circuit you throw at it, and you can like even monitor parts of the digital circuit itself. So like right, each gate, and right, kind of a cool thing you could probably see is the propagation delay as it goes through different gates, like on a breadboard setup, right? On an FPGA, that would be, of course, a little more difficult because it's all in the chip. But if you have all the I/O pins, like test points, right, to each input and output of each gate along the circuit, maybe you can see the propagation delay that way. But there's that, and then after kind of reviewing a few of my undergrad labs, at least whatever pictures I had taken at the time from at least 6 or 7 years ago, from what I understand, the labs really haven't changed, and I've kind of gone up there a few times. It's pretty much the same. Linear systems and DSP, we didn't have a laboratory course, but I could see a professor demonstrating those concepts on an instrument like this, where, right, there's the time domain, Fourier and Bode plots are kind of the key things the key takeaways that you get from those courses, as well as right Bode plots you cover in control systems as well, and I could kind of see in the control systems lab, right, like I remember we had like some fairly not cheap, right, they're pretty expensive Agilent scopes in there that we would plug in the motors, different parts of the motor or different parts of the control system like setup that we had, and we'd monitor like right, the parameters for like rise time, to see if it overshot or underdamped, right? All those parameters for all different kinds of control loops, as well as right looking at stability. And so I could kind of see it being even used for that. And then digital communications, I saw from at least one picture that we only had like a 100 megahertz Tektronix scope in the lab, in addition to, I think it was not even like a 10 or 20 megahertz function generator, which basically this model is, that covers that range. And yeah, so I've already done a couple of RF measurements with this guy. So the nice thing is 50 ohm mode is on this instrument, really great for RF. The response of the front end is not a wall, so right, it doesn't just immediately taper off right at 350 megahertz, but it's a nice gradual roll off until Nyquist. I could kind of foresee special topics courses, so like some of the ones that I've taken where there was a lab component where like sensors was one where this was technically the first course I'd ever taken that actually, for once in the entire EE curriculum, I actually got to use an Arduino, so that was kind of fun. Where, wow, I actually get to take a course where I finally get to use an Arduino that I've been using at home for many years, and now I actually get a nice grade out of it. So yeah, like right, nice thing you do with this is you can measure analog signals, right, sensors, right, measuring the world around you, and then seeing that getting converted to a digital signal, right, so you can see the full time correlated analysis with this instrument, right, so seeing how, right, from how the signal's conditioned through a bunch of op amps or whatever filtering you add, to then seeing that converted to digital domain, right, and seeing, all that full picture, as well as potentially debugging your circuit. Yeah, obviously some embedded courses, yeah, you can use the logic analyzer and the potentially the analog channels for that. That I never really took those courses, but again, I think those courses they either use like a really old Motorola development board, or I think towards the end of the course they use the Arduino. And yeah, so those are at least kind of like the undergrad, graduate level kinds of labs that I kind of foresee where like a lab manager or a professor can outfit their entire labs with just this one instrument, right? And it I think it undercuts a lot of the offerings from Keysight and Roden Schwartz and Tektronix, right? More traditional, well-established players in the academic space. I've seen more recently that um, Rigol and Siglent are now all Rigol and Siglent setups exist, and they're actually a little bit more common than I thought. At least I know from a friend at University of Florida that one of their circuits lab is completely outfitted with like I guess Rigol equipment, which I was like, oh yeah, that's fine. That's I mean it's the same controls UI and right like the menu structure is pretty much the same on the instruments as like with a Tektronix or a Keysight. What this instrument doesn't do, right? So there are inherently specialized instruments that, I mean, right, it's kind of not expected to be in a all-in-one instrument, right? You won't find a full-featured two-port VNA that goes from what like into the microwave range, right, on this instrument. That just you're asking a little too much. That will almost always be a separate instrument, right? And again, it's Wright State. We used Agilent slash Keysight VNAs in addition to Roden Schwartz VNAs in the microwave labs. And I think in the microwave sequence, I mean, yeah, that whole microwave lab is pretty much built for Intel EMAG and then the microwave sequence where you build, right, like passive networks on like circuit boards in addition to the active course where, right, now you're talking about like amplifiers, stability circles, all that, right? Like, how to actually use a Smith chart, right? And other thing that I can kind of foresee where my school didn't offer it, but I know there's a couple schools out there that offer like signal integrity, EMI, AMC courses. Not really an instrument for this. That's a very specialized set of measurements and requires completely different instrumentation, more specialized instrumentation, right? So I kind of wish looking back that, I mean, not like I could as an undergrad lobby to completely change the curriculum, right? That's asking a lot, and also that's just not inherently possible. But I wish that right, my school used the analog discovery, and then right, just in general with just more like right at the time, like I mean, all sorts of low cost tools even existed at that point. But right, I mean, yeah, hindsight's 2020, and of course, you can't change stuff that you um literally had no choice or nothing to add into the decision making process, right? That like all that stuff was well established before my time there, and I guess now as a somewhat of a let's see, how do I word this? So now, as a graduate student that might have a little pull, or at least a little bit of, what would I say? I'm now a little bit more of a bigger variable in the control loop, right, in the feedback loop for the EE department. Maybe I can lobby to get them to use more low cost and open source tools. So we'll see. Um, for sure, like this instrument, right? Like I can tell, like hopefully they'll watch this video and they'll make the conclusion that right, we can have students buy the analog discovery, they'll use this in the lab. So right, like they could do homeworks on the analog discovery at home, and then right, they can even bring then like right, they'll have their setup file for like the scope and waveform generator configurations ready to go. They bring their thumb drive to lab, plop that sucker into the computer and then load up the file, and now right, they're ready to hit the ground running in lab and make some actual like measurements. And like right, I could kind of foresee that being like a path. And I don't know, like I think Digilent actually offers like a free curriculum plan, or like a free like a pre-written set of um, like right, like they have a textbook, or like they say recommend something that's free or open source or some whatever. I know that they used to do that with the original analog discovery, and then the Electronics Explorer board at the time, they had a whole curriculum set up around it, which is very important when you're apparently right, at least in the industry that for I mean really just if you're a test equipment manufacturer trying to make it into the academic industry, you have to make sure that you have a line of like scopes that are education friendly, and then of course have all the pre-written curriculum written in advance, right? Or like at least it's just like, oh, here's a set of PDFs and PowerPoints, because right, professors don't want to do that busy work. um, so at least makes their life easier. So like right, it's like the same problem with why haven't we moved away from like graphing calculators like the TI-83 or the TI-84 or TI-89 in some aspects or some cases, because there are whole curriculums written around it, right, textbooks that are not that easy to replace, because right, that's all added cost. And so yeah, that's a kind of a part of the problem with or kind of a challenge, like, and constraint with academia, is that you have to consider all those factors. And I'm trying to remember who talked about it. Yeah, I think even Brock Ramirez from was it Montana State even talked about that a bit, where again on the amp hour episodes. So they're like, right, it's very easy from industry perspective, right, to kind of look down in academia, being like, man, why aren't these undergrads coming out of school knowing this, and that, and like, right, all these free tools exist, or these, low cost instruments, but right, I mean, like, right, all the professors have to, in their very limited schedule, have to make these decisions on. I don't know if, again, I don't know how stringent the budget is, because every time I look at the labs, right, they're able to afford Agilent and I mean Agilent Keysight slash and then even Tektronix and Roden Schwartz equipment. So I don't know how deep of a discount they're getting on those, but again, those aren't cheap, like in general. So I don't know, unless right, like Keysight just gave them like a whole slide deck, or just like pointers for the labs, right? Like, oh yeah, look, see, you just buy this whole package. You don't have to write the labs. You don't have to write the lectures. But yeah, I don't know. I'd probably have to ask around, but I at least know from at least one person, like right on the amp hour, that's actually a professor, that is apparently the case for a lot of courses, or at least trying to get stuff up to industry standards. Like again, why don't we use PCB layout tools in undergrad, or like right, or just in general across academia, is because the UI will change, right, and then now you have to write a whole set of instructions, and right, that's bunch of time to change, like right, and like it's not like you could just delegate that to a graduate student or something, right? Because again, their time is spent on research or something else, right? Yeah. So again, like right, industry wants one thing, academia produces one, and you kind of have to make that compromise. So for me, that was internships, where was the real reconciliation. Spent most of my time in school working at various engineering internships, and I definitely learned a lot more than in school as far as practical experience. for my own research, I can foresee a case where, right, you have a secure microcontroller, FPGA, you have your shunt resistor set up, you got your LNA, and then a differential probe set up to measure across that resistor. So you're looking at power correlation or differential power analysis, looking at how that's related to what's running on the chip. And this is high bandwidth enough that I think it could capture some of those like events. And then what I'm particularly interested in is the scripting aspect of this to then use the trigger output to then trigger like a chip whisper device or like a crowbar circuit or even like a electromagnetic fault injection tools like the chip shouter or something of that nature. That's something I could definitely foresee using this instrument for, especially since it's very easy to make those kinds of scripts. Like the 500 megahertz model is great for like power electronics applications where, right, instead of paying lots of money for like an actual VNA or like the Bodhi 100 or now like the new like Bodhi 500 stuff for like power analysis for switch mode converters. I mean, most of the stuff you can do with this in that frequency range, like right. This instrument's very much targeted towards that. Again, that's what the original target audience was for the NI virtual bench, where you could have a student running this whole thing either off an iPad that your school gives them or right, just off your computer. And yeah, that's something that for sure is almost exclusively students. But let's see. Yeah, next two videos I'm gonna cover from the perspective of a professional and then a hobbyist. So stay tuned for those, and thanks for watching.